Alright, logic fans, welcome to 4.13c, our third video on section 4.13. And let's pick up right where we left off. So we were translating these at most statements. What if we wanted to add a particular description? So at most one thing is pretty generic, could be anything, but at most one unicorn exists. How would I say that? And, use these as a template. Pause now. Okay, so this says, at most one thing exists, right? So what you do is you say, at most one thing exists. Sorry, scratch that. You say this. You say, if X is a unicorn and Y is a unicorn, then, then X is identical with Y. So let's take this nice and slow so that you can understand it, because it's kind of the base template for this. So this says, for anything in your domain X that's a unicorn and anything in your domain Y, if they're both unicorns, then one of them is identical to the other. And so at most one unicorn exists, right? Provided X and Y are unicorns, they satisfy this description identity. So there can be at most one, okay? And notice, of course, it's still consistent with there being absolutely none whatsoever. If you have a domain with no unicorns, easy way to think about that might be the empty domain. Notice this antecedent here comes out false, which means the conditional is true, okay? So that's basically how we would say at most one unicorn exists. How would you say at most two unicorns exist? See if you can figure it out now. Pause. Okay, so I'll get you started with a little bit of a hint, okay? But it's going to look something like this, all right? Except you're going to have a third quantifier, and you're going to say, if X is a unicorn and Y is a unicorn and Z is a unicorn, then something holds that guarantee there's not three, okay? At most two. So then what follows here? So it's going to be something like this. Okay, then either X is identical with Y or Y is identical with Z. So, provided there's, an X, a Y, and a Z that are unicorns, some pair is identical, with which basically means there can't be three, right? There can be at most two. All right? So, with that, how would you say there are at most three unicorns? Pause now. Okay, so once again, it gets a little bit unwieldy, but let's go ahead and get ourselves started here this way. So you're going to say you're going to need the four quantifiers, but after you've got that, what's your antecedent going to look like? So let's do antecedent here, consequent here. All right, and that's going to have an ending bracket on it from this bracket here, and then we're going to have the if-then. So if something, then something, which guarantees at most three. So what's the antecedent? Well, the antecedent in this case is going to be very, very similar to the antecedent here, except you're going to have four, right? If X1, 2, 3, and 4 are all unicorns, all right, then something else follows, all right? So let's get our X1s in here. Whoops. Do it this way, this way, this way, and this way, and this one's X2, this one's X3, and this one's X4. Okay, so if X1 is a unicorn, X2 is a unicorn, X3 is a unicorn, and X4 is a unicorn, then something happens, right? Some sort of description is satisfied that guarantees there's at most three. Okay, so basically what ends up happening is we can kind of help ourselves up here, but, one of these is going to be true, right? So let's go ahead and substitute this guy in there, except yeah, it should look something like that. So x1 is identical with x4, or x2 is identical with x4, or x3 is identical with x4. So basically that guarantees that there cannot be 4, there can be at most 3. Some pair among these alleged 4 are identical, okay? So at most 3. Interesting way of doing it, okay? So we really can count with identity is the point of this lesson, and on at most and at least, okay? In more advanced courses, you might cover definite descriptions. I may add some videos about that at some point, but for now, this is a really good start on being able to count with identity. Okay, so let's look at some other aspects of identity that are really, really nice, and how we can use it to basically substantially increase our expressive power now that we have this identity symbol available. So let's assume that we're thinking about a domain that's got 3 and only 3 things in it, A, B, and C, and that A, B, and C are persons, okay? All of them are persons. And so now we're going to try to translate these sentences, and you know, in a lot of them we're going to have to use identity in order to do it. So go ahead and pause now and translate this simple sentence that everyone loves everyone, and we'll use LXY to mean X loves Y, okay? Pause now. Okay, so let's go ahead and try this together. Everyone loves everyone. So what we're going to do here is we're going to say for all X and for all Y, all right, LXY. Everyone loves everyone. We didn't need to use identity to state that. But notice, as we've discussed in the past, right, this statement includes that everyone loves themselves. So this would include that A loves himself, LAA. It would include that B loves herself, LBB. It would include that C loves herself, LCC. Okay, suppose that instead we wanted to say everyone loves everyone else, not themselves. Okay, take a second and see if you want to take a stab at it. You have to use identity to figure out how you would state that. Pause now. Okay, so this is pretty interesting stuff, all right? Let's go ahead and think about this for a second. I'm going to give you a little bit of a hint. What you want to say is that provided a certain condition holds, something else holds. So for example, provided a certain condition holds, X loves Y. What's the condition that has to hold with respect to this sentence? Pause now. Okay, so this is interesting, right? What it is, of course, is that if X is not identical with Y. So let's think about this together for a second and make sure we understand why this works, all right? So this says for anything X in the domain, for anything Y in the domain, provided X is not identical with Y. So pick 2 things out of the domain. Maybe you picked the same thing. Maybe you picked different things. Maybe you picked A both times. Maybe you picked A the first time and C the second time, whatever, okay? If you picked out numerically distinct things, then those numerically distinct things stand in this relation, right? X loves Y, okay? So this is a really, really interesting way of being able to say that everyone loves everyone else, and we're excluding now, unlike this statement, the possibility of a thing loving itself, okay? So provided they're not identical, X loves Y, and it's for any X, okay? So for any X and for any Y that are not identical, this holds, okay? So this is how we construct sentences of that type. All right, let's move on to the next ones. And actually, really quickly, before we do move on to the next one, let me show you, in case you were thinking about this a slightly different way. You may have gotten it right, but you just weren't looking at it the same way I was. But recall that, you know, this really just looks like this, right? Okay, so if you were thinking about this particular solution in its transposed form, right? If it were transposed, it would look like this, right? It would look like this here, okay? And so this would be not LXY. And so you might have been thinking about it like this, all right? for all x and for all y. If it's not the case that x loves y, then x is identical with y. So if x doesn't love y, then they're identical. Okay? And these are logically equivalent, so they're both equally good as solutions. So I wanted to point that out. Okay, moving on. Let's try C here. So give that one a shot. Pause now. Okay, so we've got our three-person domain. Someone loves someone, so it's not going to be too difficult, right? But you're going to have existential quantifiers like so, and so it's someone loves someone, so there exists an x, there exists a y, such that LXY, right? So, you know, it's modeled just like A is here, except for the existential quantifier. So now, suppose, you know, because this is consistent with it, the only person doing any kind of loving is A loving himself. It's true there that someone loves someone, right? But so suppose instead you wanted to say someone loves someone else, not themselves, right? How would you state that? Pause now. Okay, so you know, you've probably picked up on them on this, but there's an x, there's a y, x loves y, and in this case you're going to say and x is not identical with y, right? So it would be just like this, okay? And you can imagine using different different tricks inside of here with negations and everything, but that's the basic idea. There's an x, there's a y, x loves y, and x is not y. So someone loves someone else. At least one person loves someone other than themselves. Okay? That's how you would state it. Go ahead and try E now. So E is a really interesting case, all right? It's saying that everyone loves someone. So if you have your three-person domain that we're sort of imagining here, all right, everyone loves someone. So A loves someone, possibly only themselves. B loves someone, possibly only themselves. C loves someone, possibly only themselves. So those are the kinds of ways in which it could be true on that on our domain. So everyone loves someone. But suppose you wanted to say every person, A, B, and C, loves somebody other than themselves, right? How would you state that? Pause now. Okay, so it's going to be very, very similar to our D here, right? So it's going to be everyone, so this is going to be the universal quantifier, loves someone that's not themselves. Okay? So this is how you would state it right here. Let's try G. Someone loves everybody. So either A loves everybody, or B loves everybody, or C loves everybody, or some combination, but they must love themselves too. So how would you state that with G? Okay, this is an interesting one. So let's go ahead and think of it this way. So someone loves everyone is going to look just like this. There's an X, either A, B, or C, that loves everyone. Okay? So it would be stated just like this. One of these guys in here loves everyone in here. All right, what about H? Someone loves everyone else. So they don't love themselves. They may or may not love themselves, but definitely they love everyone else. Okay? Okay, so this one's a little bit tricky, but we want to use the arrow here, okay? So this says there exists at least one person for any y such that provided x is not identical with any of the y, then x loves y. So, you know, you're thinking about all your possible pairs, AA, AB, AC, BA, BB, BC, and so on. And for all these pairs, provided they're not identical, x loves y. Right, and that's the way to really think about this. So, yeah, there exists an x for every y such that if they're not identical, for any of them that are not identical, x loves y. Okay, that's what you want to say there. Okay, let's carry this on to the next video. So look for 4.13C. Pardon me, 4.13D.